feedback controller, we measure control variable. And for feed forward controller, we measure load variable. Don't say here this Z is control variable. Fine. And second point he told that is correct. See here feedback. This is a feedback. Okay, but I mean the controller acts after the fact. So we are going simply in backward direction so that we can correct the deviation existed in XD. I repeat here we measure the composition and we just move backward direction or back step calculation we conduct mainly to minimize the deviation existed between XD set point and XD. But here you see we are moving forward. In fact, formally we tell that this controller, feed forward controller, acts beforehand. Before the disturbance affects the XD, we take necessary action through this feed forward controller. Anyway, we'll discuss in details this feed forward and feedback controller. At this preliminary level, I am just showing with the configuration. We'll discuss all these control schemes in details. In fact, we'll discuss with the formal definition of feed forward and feedback controller. But for the time being, I think you understood this at least. Agree? Okay. Now let us come to another control scheme. If you recall the variable classification table, I have mentioned there that the measured outputs are two types. One is primary measurement, another one is secondary measurement. I repeat, in the variable classification table, the measured output is classified as primary measurement and secondary measurement. We want to discuss that issue now. Fine. You draw this configuration, then I will explain this. First, you draw this configuration. So here, what difference you are observing? Any difference with the previous two configurations?
So the control variable is not directly measured. It is measured in
Control
terms of
variable. is not directly measured. See, capital T is temperature, okay?
Yes, sir.
Capital T
So,
denotes the tray temperature.
so
Yes,
XD is like dependent, like measured by T1, T2, and T3 using the estimator.
yes. Any reason behind this? Okay,
Probably because measuring XD will be difficult compared to T1, T2, T3.
yeah, what's your roll number?
19CH10037.
Did you register later or what?
Yes, I registered later.
Just 1 minute. 19CH. What's your name?
Rohit Shutrudhar.
Lohit.
Rohit. ROHIT.
ROHIT.
Yes.
Sutradhar.
Yes, sir.
Okay. Yes. Uh, yeah, anyone can give a better answer. Why we are going for temperature measurement? Why not composition? One of you, I think, gave this answer previously. Yes, tell.
Sir, concentration and temperature correlated.
No, that is fine, but why you are preferring temperature measurement over the composition measurement? Correlated, fine. You are true. In fact, what you are saying, the correlation is basically represented by this estimator. You see, we are measuring temperature and we are getting XD. So this is an estimator. That means one correlation is programmed here. That is true. My question is a little before of this block. Why we are preferring temperature measurement over the composition? Anyone?
Sir, maybe because measuring temperature is economically cheaper.
Good. Roll number?
19CH30034.
Any other reason other than cost? Okay. So another problem is, yes, anyone? Okay. So first thing is that, see, if you automate a process, you need to employ the measuring instrument online. It's not that you are collecting the sample, going to the laboratory, then you are measuring there, then coming back. You cannot do that because this process is continuous process. So we need to equip the measuring sensor online. I mean, continuously means with certain definitely time interval, it will give you the results. Now, first reason is composition measurement. You can note down these 2 points. Composition measurement involves huge investment and maintenance cost. First reason is composition measurement involves huge initial investment cost and operating cost. Fine. It means if you equip this temperature measuring sensor, for example, thermocouple is much cheaper compared to this gas chromatograph GC, which we use online for composition measurement. Second reason is composition measurement requires a large time over the temperature measurement. Composition measurement requires a long time compared to temperature measurement. Like if you measure the composition, it takes like 4-5 minutes. But if you go for temperature measurement, we can do it in seconds. So there is a huge difference. Now, if you go for composition measurement, suppose composition measurement takes 5 minutes. So during that 5 minutes period, the controller provides the same control action because it does not have any measured information to update. I repeat, if you go for composition measurement and if it requires 5 minutes time, then the controller provides the control action during that 5-minute period, the same old control action, because it does not have any updated measurement signal. However, if you go for temperature measurement, say every 10 seconds we can update the controller with the temperature measurement information. It means the controller can update its control action in every 10 seconds interval. Understood this? So therefore, mostly temperature measurement is preferred in industrial practice. Because of this reason, temperature measurement is preferred in industrial practice. Now what we can do, you see, we have measured the temperature by employing temperature sensors. I have shown here 3 temperature measurements because temperature measuring sensor is quite cheap. Therefore, we can measure, the temperature of a couple of trays instead of a single tray, just to capture the distillation dynamics better. I repeat, since the temperature sensor is cheaper compared to the gas chromatograph, we can measure the temperature of a couple of trays, mainly to capture the distillation top loop dynamics better. So after having this, temperature measuring measure temperature information, we just develop one estimator. It is nothing but a mathematical expression or maybe a model. So what this model does, it basically calculate the top composition based on the measured temperature. Okay, so this is, I can tell, a software, and this is a sensor. Sometimes it is called as soft sensor. You may hear this term, soft sensor. It's a thrust research area for many systems. Soft sensor. This is a sensor employing which we measure the temperature, and that measured temperature is converted to our control variable XD by developing a software. So that's why the combination of these two is called soft sensor. And rest is as usual. You see, after measuring this XD, we are comparing with its set point value in a comparator. This is error signal. Then this is a controller, inferential controller, and the control action is implemented through this reflux rate. Fine. Rest is like feedback controller. Just the difference is existed here. Okay, now question is why it is called inferential controller. I'm coming to that point. We just note down these points. Here estimator means it's a software which correlates XD and measure temperature. In this example, distillation composition XD is called primary measurement and temperature is called secondary measurement. Here our control variable XD is called primary measurement and temperature that we are measuring, that is called secondary measurement. Now why it is called inferential control? Because we infer the control variable by the measured temperature. That's why it is called inferential controller. We infer the control variable xd by the measured temperature. That's why it is called inferential controller, IC. Do you have any question? Anyone has any question? Yeah, if not, let me ask one question. You see this XD we are not measuring here, but still we are saying it is primary measurement. Why? Swarup Ranjan Mandal. One 0059 Swarup Mandal. Subrajit Bagh 10054. Subrajit Bagh 10054. Saijad Ansari 10042.
Yes, sir.
Tell. We are not measuring XD, but still we are saying this is primary measurement. Why? Anything you try, it may not be correct, it's okay. Don't know.
No, sir.
Okay, fine. Anyone can give the answer?
Sir, it was because XD is what we're trying to, XD is part of the control objective. So we're adjusting XD to the set point. So the temperatures that we're using to calculate XD are just intermediary steps.
Sir, our XD is control variable.
Hmm. So
So, sir,
why?
that's why control variable is also known as primary measurement. So that's why we are taking it as a primary measurement.
No, it's not like that. It's not like that. I want to know physically. This is measurement, but we are not measuring. Why we should call it measurement? I mean, why this measurement term is added with XD?
So because this measurement is used for comparator.
No, that we are calculating. We are measuring here. We are not measuring here, you see. We are calculating XD. It is estimated XD.
Sir, I think we are using all the temperatures which we are actually measuring, and using those we are calculating XD. That's why we are taking it as primary measurement.
Sorry, again tell.
So
We are
we are
measuring.
using we are measuring all the temperatures, and we are using them to calculate XD. So that's why we are taking it as primary measurement.
No, I did not get the answer. Let me tell the answer like this way. See, we are basically estimating XD, no? And we are comparing with XD set point. Anyhow, we are not measuring here XD. But how we can know what XD we are getting that is correct based on this control scheme? How we can know this? Because there is no measurement information on XD. Isn't it? This question is coming to our mind, no? We are trying to get desired purity, but nowhere any proof involved with this measured XD because we are not measuring. That's why what we do, we measure this XD intermittently. Maybe half an hour interval or maybe 1 hour interval. Okay. It may not be online. We may collect the sample and go to our lab and check whether XD is correct or not. Got the point? To verify our control scheme is performing well, we measure this XD intermittently, maybe half hour interval or 1 hour interval. That means some measurement of XD is involved. That's why this is primary measurement. Okay, in fact, one of you told that this is control variable. That is somewhat true. This is control variable. Therefore, the primary term is there because our primary concern is involved with this product purity. And we are measuring, that's why that intermittently. So this is the primary interest. This is intermittent measurement. That's why we are calling it primary measurement. Okay. So all the variables which we discussed in our variable classification table are discussed here. So I think it is clear to everyone. And you note down these questions. Few questions I am giving you. You solve these questions. Shukda Prasad Murmu, 10056.
Yes, sir.
Did you understand?
Yes, sir.
You do not have any question?
No, sir.
Okay, good. You just omit this word. No continuous measurement, no? You write here no measurement. I repeat, here it is written when no continuous measurement, but you write here when no measurement is shown. Do not use this, do not include this word continuous.
Sir, I had a question.
Yes.
If we calculate T1, T2, and T3 to calculate XD, and then we use that as the control variable, why don't we directly use T1, T2, T3 as the control variables?
That is also possible. That is also done.
Okay, sir.
That is also
So-
done continuously because temperature and XD, they are correlated, you know.
Yes, sir.
And that
Okay,
correlation is shown in the estimator.
Okay, sir. Got
Yeah.
it.
But in that case, the control scheme is called feedback controller, not inferential controller. So just to show the inferential control scheme, I have added that software or estimator part.
Okay, sir. Got it.
Yes. So you try with all these examples. Okay, distillation bottom section I did not show. You try with that. Controlled variable, manipulated variable pair I already mentioned. So it's not difficult. Conventional way you develop the control configuration. Similarly, heat exchanger you take and try with this example. I have given the answer of this question, and you consider a jacketed CSTR and develop the control configuration. It is same with the distillation column because concentration and temperature are involved. So this is quite similar with the inferential control configuration of distillation. Okay, and in fact, I have discussed, we have discussed the concentration and temperature correlation also. So estimator can be represented by that equation, modeling equation. So this is over. Now we'll come to another part. This one. Next, we will discuss hardware of a control system. We'll discuss the hardware of a control system. Okay, just you draw this example system, because our discussion, with the discussion, we'll take this example to understand better. In fact, there is nothing to understand. It's very straightforward, but still, let us consider this simple liquid tank system, which we discussed before. So first one you see, first one is this process, liquid tank system. So that's why our first hardware element is the process. It's basically an open loop process, you know. It's an open loop process. Okay, for this example system, it is this liquid tank system with its inlet and outlet flow rate. That's it. Next, what we are doing, we are measuring the liquid height, you see. So our second hardware element involved in a closed loop system is the measuring sensor. Second hardware element involved in a closed loop system is the measuring sensor. So based on our previous discussion, we can tell that the load variable we measure for feed forward controller. Control variable we measure for feedback controller. And secondary measurement is involved in the inferential controller. We have discussed these three control schemes: feed forward, feedback, and inferential controller. In case of feed forward controller, we measure load variable. For feedback controller, we measure control variable. And for inferential controller, we measure secondary measurement. Fine. Next is our, let us detail these sensors. This is a detail about variable and the sensor used for measuring the respective variable. Just few are listed here. For temperature measurement, we go for thermocouple, RTD. RTD is, what is RTD? Resistance temperature detector. RTD is resistance temperature detector. For pressure measurement, we usually go for manometer. Pressure gauge. These are used for pressure measurement. For flow measurement, there are several flow meters like Venturi meter, orifice meter, pitot tube. Did you study any flow meter, student?
The pitot tube and venturimeter.
Did you study?
Yes, sir.
In which course? Fluid mechanics or mechanical operation?
Sir, last time we have fluid lab, so in that we
Okay.
started.
Okay, good. So you know something about this. These are flow measuring device. Venturi, orifice, pitot tube. For liquid level, this differential pressure cell is extensively used in practice. Differential pressure cell, I have given hint. This is just del P equal to H rho G. Based on this concept, it measures the liquid level. And for composition measurement, we go for chromatographic analyzer, gas chromatography, GC. This is popularly called as gas chromatography. Fine. And I want to mention here that these will be discussed actually under instrumentation course. All these will be taken care of under instrumentation part of this IPC course. Okay, but I'm just mentioning here. Along with this, you will study also control valve. Fine. Okay. Let us come to the next point, that is transducers. Many measurements cannot be used for control until they are converted to physical quantities. Physical quantities means like electric voltage, current, or pneumatic signal. I repeat, many measurements cannot be used for control until they are converted to physical quantities like voltage, current. It's very simple, like you are measuring temperature. Your measuring sensor is displaying temperature, but this temperature you cannot transmit through the wire to the controller, isn't it? If you want to transmit this temperature information to the controller through the wires, you need to convert them to these quantities, either voltage or current or pneumatic signal. Now for this conversion, we use an instrument that is called transducer. In fact, nowadays, you know, with the measuring sensor, this transducer is integrated. So you cannot see them separately. With the measurement sensor, this transducer is integrated. So that's why if you recall, I have shown CT, composition transmitters. Okay, that means it measure composition and transmit also. That's why CT, PT, TT in brief, or it is denoted by those terms. Fine. And I think you know this pneumatic signal. Pneumatic signal is if you consider I'm just giving you one example, control valve. So for control valve, this pneumatic signal varies from 3 to 15 psi gauge pressure. When you are giving 3 psi pressure to a valve diaphragm cell, then the valve is completely closed. I mean 0% open. If you give 15 psi, the highest signal, then your control valve is 100% open. So this is pneumatic signal basically. It is in terms of air pressure. I'm just giving the example for control valve. It is 3 to 15 psi gauge pressure. Anyway, this will be detailed in instrumentation part. Next is transmission line. So we have measured the temperature. We have converted to suppose voltage. Now we want to transmit that voltage from measuring sensor to the controller. So for that we need a transmission line. I repeat, say we are measuring the temperature by a measuring sensor. Then we are converting that measured temperature to voltage by using a transducer. Then that voltage we want to transmit from the measuring sensor or transmitter combined system to the controller. So for that we need one transmission line. Okay, transmission lines are used to carry the measurement signal from the measuring device to the controller. Okay, in the past these transmission lines were pneumatic. That means it was transmitting like compressed air, compressed liquids. But nowadays, most of the cases it is electrical signal. It may be voltage, it may be current, like that. Okay, as I shown just in the third step. Now this signal may be very weak, few millivolts, and cannot be transmitted over a long distance. In such a case, the transmission line is equipped with amplifier. In such a case, the transmission line is equipped with amplifiers. Next part is the controller. You recall all the times the liquid levels example, which I have shown at the beginning. So process, then measuring device, then transmitter, then transducer, then transmission line. Then we reach to the controller. This controller receives measurement information from sensor and it calculates the control action. Okay, it calculates the control action. Next one is the final control element. So the control action is basically implemented through this final control element. Estimated or computed control action is physically implemented through the final control element. Like we have used so far, I think, control valve. But it may be variable speed pump, variable speed compressor, switch, etc. Okay. For variable speed pump compressor, they have variable RPM. Okay, so we can change their delivery according to the control action. That's why they are called variable speed. And last one is the switch. What do you think about the switch? I mean, switch is what type of controller? Any idea? Switch is what type of, which switch falls under which type of controller? It's a on-off controller. Okay, it's an on-off controller. There is no intermediate action, either off or on. Last one is the recording device. Last one is recording device. It is usually used to visualize and record the plant behavior through measurement signal. So if you are going for your industrial training, you'll see that they have one control room. So that control room basically shows the plant behavior. Okay. In fact, the measurement signal they show with time. Like if you consider liquid tank system, the control room, in the control room we can see how the height is varying with time. Okay, so that is basically concerned with this video display unit. Fine. Now one important term which is widely used, that is direct digital control or DDC. So what control configuration we have discussed so far, that is basically direct digital control. Okay, you know, down one by one, you can easily understand. We have discussed the issues so far in details. We directly receives the measurements from the process by employing a sensor, online sensor. Then based on this measurement signal, we calculate control action for manipulated variable based on the control law programmed in the computer. You remember that the comparator, I mean calculation of error signal, set point minus measured, and controller equation, these two are programmed in a computer. I repeat, the comparator, where we compare the set point with the measurement signal to calculate errors, and the controller equation, these two are programmed in a computer, and that computer basically acts as a controller. Okay, then the control action is physically implemented through the final control element FCE. The direct implementation of the control decisions gave rise to the name direct digital control. This direct implementation of the decisions gave rise to the name direct digital control. Arjav Rastogi, 10011. Can you hear me, Arjav Rastogi? 10011. Aditya Agarwal, 10005.
Yes, sir.
Yeah, you tell me what is programmed in the computers. Which equations? You know this or not?
No, sir, not
Yes.
the equation.
Just now I told. Abhishek Purohit 10002.
Yes, sir.
Tell me, what is programmed in the computer in this DDC
Sir,
system?
sir, the first equation is control objective equation. That is like set point minus the measured value, and the second one is comparator.
That is comparator only, no? Set point minus measured value is calculated in the comparator only.
Yes, sir.
Anything else? Abbas Sarkar 10001 17CH. Abbas Sarkar.
Yes, sir.
Yeah. What equations are programmed in the computer for this DDC? You know or not?
No, sir.
Okay. Lalit 10020. Lalit. Kumari Bhavna 10019.
Yes, means it
Tell.
actually calculates control action using the computerized programs.
Anything else? Only one or other equations are also programmed?
Other equations can also be programmed, like I can give the examples. For example, if we are measuring temperature with the help of a controller, then we will be having a temperature set point and a measured temperature. So the computerized program will calculate the difference between it in order
Yes.
to fulfill the control objective.
Correct. Correct. So I will give 5 minutes gap, or we will continue and I will leave the class a little before. What do you like? Okay, let us take 5 minutes leave. We'll again meet at 11. Okay. Okay, so let us continue our discussion. This is all about hardware elements. Next, our topic is mathematical modeling. Our next topic is mathematical modeling. Okay. So what usually we do, we have an experimental setup. We give some input to this experimental setup. You can say raw material we introduce, and then we get some output from that experimental setup. Fine. By this way, typically we do our laboratory experiments. I repeat, we have an experimental setup. We give input to the experimental setup and we get some output. Now, what we want to do, we want to represent this experimental setup by some mathematical equations. We want to develop some mathematical equations or expressions or combination just to represent this experimental setup. You see, I have shown that. This block basically includes the mathematical equations which represent this setup. Now we are giving the same input and we are getting some output. Usually these two outputs are never identical. In practice, these outputs are never identical. Hope you got this concept. This is the setup. These are the mathematical equations which represent this setup. We are giving the same input, but we are getting the different output. Now, if these two outputs are close, in that case, we can say that our mathematical equations are reasonably correct. I repeat, if these two outputs are close enough, in that case, we can tell that our mathematical equations are reasonably correct. or our model is reasonably correct. This is basically the model, you know. Mathematical equations are basically the model equations. Okay. So for a good model, both the outputs should be close enough. But never expect 100% matching. It's never possible in practice. So how we can define this model? This is the formal definition. Note down this formal definition. A real system is mathematically represented by a model. A real life system is mathematically represented by a couple of equations. Those equations constitute the model. Fine. Now this is model. What is simulation then? Modeling and simulation we know, no? What is simulation? Anyone can give the answer? I told the model part.
So simulation is testing that model in some virtual environment to see the accuracy of that model.
Better way. Can anyone tell in a little better way what is simulation?
Sir, is it a way to check whether the model is close enough to the real experiment?
This is testing. Why you are saying that is simulation?
So by simulating the model, we can.
What is that simulation? That I want to know. You are saying no, simulating the model. What is that?
Sir, observing the values based on some time scale.
This is observation. See, simulation is a solution of modeling equations. That is simulation. In numerical methods, we have used this term numerical solution, but here simulation. Okay, simulation we use because a large number of equations are usually involved, and for a long time we produce the results. The simulation is basically the solution of model equations. That is simulation. Okay. So modeling and simulation, these two terms are clear to us. Simulation is basically the solution of model equations. And for chemical processes, this model consists of a couple of equations. Even, you know, combination of differential equation, algebraic equation, they are there. And we usually observe the variation of different variables, particularly output variables, with time. So it's not the calculation for a single time step or 2-3 time steps, what we have started in most of the cases in our numerical course. Fine. Now let us come to the types of models. So there are two types of models. I mean, we can classify the model in different ways. Now here it is classified based on how they are obtained. So let us start with the classification of models with this theoretical versus empirical model. Theoretical model is developed based on conservation principle. Theoretical model is developed based on conservation principle. Rahul Nath, 10033. Rahul Nath, 10033. Sahil Boiragi, 10040. Sahil, can you hear me? 10040. No. Sanskar Patni, 10046.
Yes, sir.
What is conservation principle?
Sir, I think it's based on what the theory says. Not any experimental steps have been performed, but what we have theoretically derived. It's based on that.
Conservation principle, you tell directly. You have started in your chemical process calculation course.
Like conservation, like energy, or something like that. Conservation.
Yes, correct. Conservation of mass, conservation of energy, conservation of momentum. Those are conservation principles. Yes, okay. So if you apply the conservation principle and get the modeling equation, then that model is called, the resulting model is called theoretical model. Fine. And anyone can tell what is empirical model? Anyone? Yes.
There are some corrections required in the theoretical model. Like for an example, it will be a very vague example, but like if something sticky mass is flowing through a container, and it may happen that some of the mass may get attached to a container, so the mass conservation principle at the input and output may not be valid. So we have to apply some empirical model to justify our
Now you were
theoretical
saying perhaps
conclusions.
why we need the empirical model over theoretical model. You give a simple example, empirical model we are using in our chemical engineering civil courses.
So sometimes the theoretical model gets really
Do not give the
complicated.
reason. I am asking the example of empirical model. Reason we are coming after some time. Yes.
Square method.
Tell.
Least square method.
Least square method. Correct, empirical model. Are you using any expression, any empirical model? I hope you have used.
Sir, enthalpy calculation.
Equation balance.
Correct, enthalpy calculation. What's your roll number?
19CH3FP07.
Ronak Agarwal?
No, sir, Yashvi Jain, 19CH3FP07.
I think you have registered late or what?
Sir, my roll number is last in the list. 3FP, not 300.
I got. What's your name?
Yashvi Jain.
Jain.
Yes, sir.
A Jain. Can I write?
Sir, Yashvi.
Rasmi, okay. RASHMI?
Sir, Yashvi, YASHVI.
YASHVI. Jain, JAIN.
Yes, sir.
Okay. Yeah. Enthalpy equation you are using, that is empirical correlation. In fact, CP you are using, heat capacity, A plus BT plus CT square plus DT cube. This is empirical model. Okay. Now, empirical model is basically based on the input and output data set. If you have the input output data set, you can develop easily the empirical model. I have shown this figure, no? Here input is there, I am getting some output. So input you know definitely because you were giving, or if not, you can measure it. Output you measure and just make one table, output versus input. Then you can develop one model that is called empirical model. Any other example? Any empirical model in reaction which you are frequently using? Arrhenius equation. That is empirical model. Fine. Now come to yeah. Someone also told how we can make these least squares and in better way, or maybe for the large systems we can go for this artificial neural network, which artificial intelligence covers this artificial neural network. So anyway, these two are based on the input-output data set. This example someone told enthalpy A plus BT plus CT square. You have started this equation where, in which course? Dietz-Boelter equation?
Sir, in
Heat transfer.
Heat
Heat
transfer.
transfer. What type of heat transfer?
Convective heat transfer.
Conductive?
Convective.
Convective. Yes. So this is empirical equation. Sidat-Tate equation, Dietz-Boelter equation. Okay. So these are based on empirical model. Now this is the semi-empirical model. Yeah, hybrid model. Combination of the above two. So in majority of the cases, you will see that we are using this hybrid model. In majority of the cases, we are using hybrid model, but still many people call that, theoretical model instead of this model. I repeat, for most of the chemical processes, we obtain finally hybrid model or semi-empirical model, but usually the people do not call it hybrid model. They usually call it theoretical model. Like if you go for reactor model, we develop the we apply the conservation of mass to get the concentration equation. Then we apply the conservation of energy to get the temperature equation. And then we use Arrhenius equation, which is an empirical model. I repeat, for a reactor, we first go for conservation of mass. We apply the conservation of mass principle and we get the concentration equation, differential equation. Then we apply the conservation of energy and we get the temperature differential equation, dT dt, T capital T, D small t. And we also use Arrhenius expression for pre-exponential factor K. So it's basically a hybrid model or semi-empirical model, but people usually call it as theoretical model. Okay. Now come to the advantages and disadvantages. I think you are trying to say, many of you are trying to say, what are the advantages of theoretical model? Anyone? What are the advantages of theoretical model?
It is most precise.
Like most precise. I mean, you want to tell more rigorous?
Most precise in the sense that the numbers that we get from that model will be like the most accurate out of the
More toward ideality.
Yes, more towards
no, we cannot say all the times. Sometimes say let us finish one by one issue. Sometimes we go for empirical model. No, that means in that case theoretical model is not predicting oil, or maybe it's very weak. So all the times we cannot say theoretical model is outperforming empirical model. But you can tell the term that what I told, it's rigorous. Rigorous in the sense it can capture, it can give physical insights into the process. Yeah, someone was telling another point. Please carry on.
Sir, they are more universal.
Like they're applicable
Universal.
to wider range of values.
Tell
Like the
what?
The values that we get are like applicable for like more conditions. I'm not like wider range of conditions.
Yes. What's your roll number?
30018.
Who told universal?
Sir, I too.
Roll number?
19CH30029.
So it is also somewhat okay. I mean, we can say that it is applicable to a diverse or wide range of conditions. Fine. Explanation is somewhat like this. For the empirical model, you are using input-output data set. Suppose input-output data set you have taken for a particular condition. And based on that input-output condition, you have developed the empirical model. Now, whenever you are going to use that empirical model at a different operating condition, you may not get satisfactory result. I repeat, empirical model is developed based on the input-output data set for a certain conditions. Now, if you go to use that empirical model for a different condition, you may not get satisfactory performance. See, I am telling may not. You cannot reject that it cannot perform satisfactorily for other conditions. It may perform, but most of the cases, it yields a large deviation with the actual value. Yes. And what about the drawbacks of theoretical model? Any drawback?
Sir, more number of measurements are to be performed.
More number of
Measurements for different variables.
So there may be
Takes
some
time. It
quantities
is
which are not readily available with us, and we need to perform some experiment to get those values.
Which values?
Sir, like heat conductivity or something which we are using in our theoretical model, we need to first find out if they are not readily available.
Okay, I got. Yeah, roll number.
So 19CH10002.
Yes. Few variables we do not know, and in fact, what you are saying, we go for them empirical model like heat transfer coefficient U. Mass transfer coefficient, we need this information in the theoretical model, but in case of empirical model, all these are not required, just output variable we need.
Because we have
as
to
it is towards as it is more towards ideality, and we can play with wider range of conditions, so it may be time consuming to prepare theoretical models.
Good. Roll number?
So 19CH30024.
Yes, this is correct. It's time consuming, especially for the large systems, okay, which is quite common in chemical engineering. It is time consuming. And yeah, anything else? One important point I am not getting.
So, like you said, they can be very large. It can be very large, so this can increase complexity of the model.
Yeah, that is obvious. If it is large means usually complexity, not only for modeling, also for simulation, we face some at least more tedious work we need to do, or yeah, more time we need to consume to develop the model and for the simulation, for which we need to develop the code, computer code. For modeling, for simulation, both the cases we need to consume, we need to spend more time compared to empirical model. That is obvious. Anything else?
So it may not account for the practical restrictions or the limit that can happen while performing the experiments.
For which case? Theoretical.
Yes, for theoretical.
Yeah, that is obvious. We have already mentioned, no, it is applicable to a wide range of conditions. In fact, for condition at which we did not do the experiment, there also we can use this theoretical model. Anything else? One important point is missing.
It is difficult to account for all the losses and frictional losses and other random disturbances that can happen during the process.
That you can take care of in the theoretical model. That you can take care of theoretical model, no? An empirical model, they are reflected through the output. What's the problem? Yes, someone else was trying to tell something.
Sir, yes, sir. Some variables may not be directly available to us.
Which variable?
Like heat transfer coefficient or mass transfer coefficient.
Yeah, for them I mentioned, no, you can go for empirical model. So ultimately it's a hybrid model. That's fine. Heat transfer coefficient, mass transfer coefficient, those may not be readily available to us. Particularly for a new process. For old processes you can get from the textbook, but for a new process, you have to find these parameters. Latent heat, heat transfer coefficient, mass transfer coefficient. Anything else?
Sir, there are some constraints on theoretical model, like the flow should be inviscid, which are not possible in real life. So that's the drawback of theoretical model.
So I think you were saying about the assumptions. Okay?
Yes, assumptions.
Yeah. So initially, for all theoretical model, we need to adopt a couple of assumptions. And then we are gradually relaxing those assumptions to make the model more rigorous. That is always true. That's why someone told, no, it's close to ideal or something like that. We cannot say what type of model you are developing. If your model is rigorous, then we can have better results close to the actual output. But if your model is not good enough, even theoretical model, no, if you have so many assumptions, in that case you may not get even the desired output. See, one important point what you are missing that I want to tell is that in the theoretical model, the phenomena of a process are taken care of. Okay, particularly if you are going for a rigorous model development, in that case you have to address most of the practical concerns, most of the practical issues, most of the phenomena we need to include, you need to address in the theoretical model. Fine. And like for a particular process, if you simulate a theoretical model, no, so individually you can see, like if you want to say temperature, how it is varying with time, that you can see. At the same time, you want to get the information of concentration with time, that you can get. If you want to see what is happening in terms of, say, K, for which we are using Arrhenius law with time, that we can see. So physical insight we can get from the theoretical model, but from the empirical model, you do not have scope to get the physical insight of a process, because the value we are getting from an empirical model, that is only in terms of output. What is happening in terms of any intermediate variable or other variables, you cannot have any idea. Fine. So in brief, I can tell, theoretical model provides physical insight into a process. Empirical model cannot give us physical insight. Okay, this is an important difference. Okay, so these are advantages and disadvantages. You see what we discussed, they are coming with these points or not. This is the advantage of theoretical model. And you see the advantages of theoretical model are basically the disadvantages of empirical model. And same thing is applicable for this term, disadvantages. Disadvantages of theoretical model are basically the advantages of empirical model. You just check whether they are matching or not. This HTC is heat transfer coefficient. Okay, heat transfer coefficient, mass transfer coefficient. This is lambda is latent heat. HTC is heat transfer coefficient, MTC is mass transfer coefficient, and lambda is latent heat. I think almost same thing I have repeated here. So I hope this is clear to everyone. Okay, it does not extrapolate well. So it is applicable to a limited range of conditions. And we do not have any physical insights into the process by this empirical model. Just I have given one example, although you know it is not yet taught distillation, but you just note down this, and after covering distillation you can easily understand this part. In fact, I will discuss also the development of distillation model for you. At that time you can understand this. Just note down. What I have written in the first point, empirical model finds temperature without having information on M and X. M is the liquid holdup on the tray. M is the liquid holdup over the tray, and X is liquid phase composition. Okay. So empirical model directly develops the correlation in terms of output T. It cannot provide the information individually for M and X. We do not know about these two. If you want to know even, you cannot get from empirical model. But if you go for theoretical model, it develops the model not only in terms of temperature, but also in terms of tray holdup and X. In fact, this tray holdup and tray composition information is required for the development of model in terms of temperature T. So if you want from the theoretical model, the distillation dynamics in terms of temperature, M and X you can have. you can see that. I repeat, from the theoretical model, you can see the dynamics of distillation in terms of temperature T, hold up M, liquid composition X. Okay, dynamic means temperature versus time, tray hold up versus time, X versus time. All information you can have. That means we can have physical insight into the distillation process. Okay, this is one typical example. Now come to the simulated model. So first we develop the model, then we solve those modeling equations, which we call the simulation, or we can say that simulated model. I repeat, first we develop the model for a particular process, then we simulate or solve those modeling equations. So this we can tell as simulated model. This is known as simulated model or maybe simulator. Now question is, what is the need of this simulator? Why we need these simulators?
We can make controllers based on the model.
How you know this? Although your answer is correct.
Sir, because the solution of the model dictates how we control the variables, manipulated variables.
See, if you recall the feedback controller, suppose we have measured the control variable, and that measuring information is going to comparator, followed by controller. So we don't need any information other than measured control variable. So why are you saying model we need? Got the point? If you recall the control configuration, we measure the control variable, and that information is enough for the controller to calculate the control action. It does not need any model. But still I am telling your answer is somewhat correct. See, there are few controllers which are called model-based controller. For those controllers, we need process model. I repeat, there are a couple of advanced model-based controllers. For them, we need process model. Okay. Anyway, any other answer?
For verification.
Verification. I mean, you were saying validation?
Yes, sir.
See, validation you are doing for your model. I mean, you are checking whether your model is correct or not. That's why you are going for validation with experimental data. But this is not really the direct answer of my question. You are validating your model to check the accuracy of your model. But my question is why we need the simulated model?
Sir, for like increasing the profit.
For
obvious economical benefits.
Yes.
Like.
Yeah, correct. What's your roll number?
Sir, 19CH10069.
Yes, this is correct. For economic evaluation, particularly for calculating the profit, we need this process model. So two correct answers I got. One is for controller development and second one is for calculating the profit or economics analysis. Yeah, first point I have written here, you see. Improve understanding of the process. Let me explain this point. Suppose you have one experimental setup and you have developed the process model, but you did not experiment you did not perform experiment in all the conditions. It's not possible also because it is, you know, cost is also involved there, no? So we cannot do perform experiment in all conditions. So what usually we do, we perform the experiment for a certain condition. We develop the model and then we validate our model with those experimental data. Once we confirm about our model performance, we use that many other conditions at which experimentation is not done so far. Got the point? I repeat, we have one experimental setup and we did the experiment at 2-3 operating conditions. We cannot do the experimentation at a wide range of conditions because it's, you know, cost is involved there. So anyway, we did the experiment at certain conditions. Then we go for modeling, followed by simulation. Then usually what we do, we test our model or simulated model, whether it is correct or not. How we test? We just compare our output and experimental output. Once we are confident about our model, we extend the applicability of our model at various other operating conditions at which so far no experimentation is performed. Okay, that is what written here, improve understanding of the process. Not only at different conditions, we can also understand or see the dynamics at different other variables. See, in the experiment, we can measure 2-3 variables. We do not go for the measurement of all 10-15 variables. It is again, you know, I mean, cost is involved there. So we measure 2-3 variables and rest 8-9 variables we usually see in terms of our model output. I mean, we see our model predictions. So that's why this first point, improve understanding of the process. Second one is train plant operating personnel. See, if you are going to join in process industry, first you will see that they are providing a training to you and you are called trainee engineers. Now during that period, usually they introduce the plant dynamics, operation, safety, all these aspects by visiting the different units. Okay. I repeat, when you are going to join in process industry, at first you are provided the training for maybe 6 months or 1 year, something like that. And during that period, you are called trainee engineers. In fact, you need to visit the plants, you see the operation, etc. But apart from that, you know, there are certain abnormal situations which you never experience in the real time in your visit. There are several abnormal situations, dangerous situations, which you do not face during your visit. So those abnormal situations, dangerous situations, are basically experienced by running the simulated model. I'm just giving you one example. Suppose there is a pump which is delivering the liquid to a process unit. Suddenly that pump is not working. What will happen? In a distillation column, the tray is flooded with liquid. What will happen? In a distillation column, suppose one tray is disintegrated in the tower. What will happen? All these issues are properly addressed. All these issues, I mean, we can have some experience against all these situations through the simulated model. Okay. So along with the normal situations, some abnormal situations also are experienced by us through this simulated model, because it's not like that you will have some experience with normal condition. Mostly the engineers or experts need when the situation is not normal. So the training engineers should have some experience under such abnormal situations, and that we can do by running the simulated model. Okay. Third one is selection of control pairings and tuning. Although I have tried to convince you through physical understanding how we can make the pair between control variable and manipulated variable, but originally, the control variable and manipulated variable, they are selected by performing some analysis. Okay, and that analysis is done by using the model. And it is beyond the course, beyond the scope of this UG course. It is taught in master's level, advanced process control, especially, the 12 degree students, they will read this course, advanced process control. So there we discuss this selection of control variable, manipulated variable pair theoretically. And there we need the model. Okay. And tuning, controller tuning requires the process model that we will discuss in this UG course. Controller tuning requires the process model that we will discuss later. Fourth point already discussed, development of model based controller. The name itself suggests that this controller requires process model. And these are advanced level controllers, and again, this is out of the scope of this UG level, but you just note down. For the development of model based controller, we need process model. The name suggests so. And fifth one, already someone told that to optimize the process operating conditions, we need process model. That's it. If you have any question, you can ask me, otherwise we will end here. Any question? Okay, thank you then.
Thank you, sir.
Thank you to everyone.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you to everyone.
Thank you, sir.
Thank you.